Welcome everybody to the Complexity Colloquium. It's my pleasure to introduce Dashun Wang. He's a professor at Northwestern University in the Kellogg School of Management, and he's the founding director of the Center for Science and Innovation. And he's also core faculty at the Northwestern Institute of Complex Systems. And he recently published a book together with Laszlo Barabashi on the science of science. So it's he will speak about this, but by his book, it's I highly recommend it. But he will give us a tease, and then you'll be able to satiate your curiosity by reading his book. So Dashun is well-renowned in the field of complex systems. He recently won the Complex Systems Society Award for what's the name of the award? Well, the award that the Complex Systems Society gives for advances in complex systems was given to Dashun. So well, I could speak a lot about his contributions to complex systems, but I'll better let him speak us about science of science.
All right, thank you. Let me share my screen. That's the most important part. All right. Then hopefully you'll see this. All right, so see my screen okay, Carlos? All right, okay, so hey everybody, great to be with you all. I'm the recovering physicist at Kellogg School of Management and also the McCormick School of Engineering, where I founded and currently direct the Center for Science of Science and Innovation, which is dedicated to this area of research called, many of us call science of science. What I'm gonna do today is actually take a new approach to giving this kind of presentation, where to think about the audience as not somebody working in complex system or science of science per se, but thinking of the audience as just everyday scientists, and think about what are the distilling lessons as I present these findings and insights from the science of science. I want to also sort of hopefully will offer sort of some of the lessons that we can learn as a scientists. So let me give you a quick intro, 1 minute intro on what is science of science. 2018 was a great year for the field, where we published the first review paper of the field called Science of Science in Science. Later that year, Science also put out a special issue, putting us on the cover, arguing to write a more scientific science. And earlier this year, we're also excited about the publication of the book that I co-authored with Laszlo Barabashi. Was published in Cambridge University Press. So what is science of science? So in many ways, this idea of turning the scientific methods and curiosities upon science itself, this is not a new idea, right? This idea traces back to at least mid-past century. And there are several founding giants of the field, including Robert K. Morton, thinking about the idea of Matthew effect, singletons and multiples. The Solar Prize, thinking about the idea of invisible college, power loss, cumulative advantage, or Harriet Zuckerman, with another sociologist of science, thinking about the ethnography approach toward understanding scientific careers, using Garfield, information scientists, thinking about citation index, or of course, there's Thomas Kuhn, one of the greatest thinkers of 20th century, thinking about the idea of paradigm shifts. So in many ways, I think the current surge of interest in understanding science is to stand on the shoulders of these giants, but they then take two things that they did not have the luxury to have in their time. The first is the increasing availability of large-scale data sets that trace the entirety of the scientific enterprise, helping us capture its inner workings at a new level of scale and detail. I can't emphasize enough how exciting, how much new data sets are becoming available. Let me just give you one personal example. If I look back at the research from my own group over the past 5 years, it's safe to say every year our research agenda is shaped by a new data set just became available that we didn't even think was possible a year before. This is true this year, it was true the year before, it was true the year before that. Earlier this year, we published a paper in Science that was based on data sets that wasn't even available before last summer. So this sort of illustrates the level of excitement around the field. And second, I think is the parallel remarkable developments in fields like complexity science, networks, artificial intelligence over the past decades, which offers us a wide range of tools that help us make sense of this data with growing accuracy and robustness. Together, they tell a complex yet insightful story about how innovative careers unfold, how people can come together and collaborate and contribute to discovery, and how scientific progress may emerge from interconnected factors. So what I'm going to do today is to give you sort of a sample or several range of researches, so that first of all, they give you a flavor of type of research we do. And second, in doing so, hopefully also offer you some useful lessons from the data and sort of thinking about your own career developments, especially for junior researchers in the audience. All right, so the first line of research I want to talk about is what I broadly call the HOPE project. So this is the idea of thinking about, if we have all this kind of a career histories of scientists, can we think about, can we understand some patterns, reproducible patterns of a promising career? And this is what I call the HOPE project, because I just want to think about, when do you produce your best work? Is there hope left? Will you produce a better work after a major discovery, or are we dead, scientifically speaking? Okay, so one way to think about career is to think about this drop pin view of a career, where we say every time you publish a paper, I put a drop pin at that location at that year, and then the height of the pin will tell me how good these papers are, approximated by, for example, citations. So if I represent careers by all this view, then it's very simple, is to say, where does the highest pin occur within a career? So this is the question that has fascinated psychologists or economists for several decades in the past. And the conclusion is very simple and robust, is that when do you do your best work? You do your best work in your mid-career, somewhere around 30 to 40 years old. And the reason is that, it's quite simple, is that there's no 4-year-old has ever won the Nobel Prize, because in the beginning you have to learn. And then as you get older, there's growing responsibilities and duties piled on your shoulders, reduce the time you have for research. So we repeated this analysis, finding something similar. And sort of a characteristic curve here is to show, as you get older, there's this gradual, if brutal, decline in terms of whether or not you'll be able to produce a major hit. So this seems to be quite pessimistic, but one thing we did with this was, let's do a simple operation with the data. Let's take the job pins and start randomly swapping them within each career. Okay, so for each career, I'm gonna take 2 job pins. I'm gonna swap their location. I'm going to keep doing this for all the different pairs of job pins. And so what am I doing in that operation? Because I'm just swapping the pins, so I'm not taking away any pins. So I'm keeping the productivity fixed. I'm also keeping the distribution of the height of the pins fixed. All I'm changing is where your best work occurs, right? Imagine you have a deck of cards and you have ace in that card. All I'm doing here is to shuffle that card. So now the timing of that hit becomes random. And so now I can remeasure when do you do your best work within the shuffled deck of cards. And that's where you find that for the randomized careers, they too follow exactly the same pattern as what you measured in the data. All right, so this would mean that actually what this curve we're seeing is primarily driven by how productivity is distributed across your careers. And so what it seems to be then, your best work actually within the body of your work, within the sequence of your work, it actually occurs randomly within that sequence. In other words, it has the same probability to be your very first work, or very last work, or somewhere in the middle. So before I get too excited, so let's actually push on the robustness of this finding and think about, whether this is true. through other kinds of careers as well as other definition of hit works. In this case, we actually sort of expand the scope of analysis to think about, okay, by analogy to scientists, what about artists? So we collected about a couple of thousand, 3,000 artists over the past 500 years, roughly thinking about their artworks they produce along their career and then auction prizes for those artworks. We also look at directors over the past 100 years, recorded in the IMDb database to think about, movies they produce and the IMDb ratings of those movies. Across all these careers, we can measure when do your best work occur, and I'm going to measure this cumulative distribution for the order in which it occurs within the sequence of the work one produces. So what you see is a clear diagonal pattern. So this sort of confirms this idea that what we call random impact rule appears rather robust, is that your best work seems to have an equal probability to be distributed, randomly distributed within your body of work. And what about not just your best work? What about your second best work, or third best work? And if we do that measurement, we see a very, very similar pattern. So what this tells us is this idea that, you're more likely to break through, during your mid-career. And this is not because age and creativity are intertwined. It's simply because you produce more during your mid-career. So some people take this as a rather hopeful message, is to think about as you get older, on average, it seems like your chance for breakthrough start to drop, but that's not really because that you are less creative. Per production, the hit rate appears remarkably constant across a career. So some people take it as feeling, if you keep producing, your best work may be yet to come. Okay, and then this is not just your best work, but also true for your second best work and third best work. Now, one question here is, it raises also a deep puzzle to me, because it seems to me to tell me that career is just like a lottery ticket. Every time we produce something, it's all random. We don't know when we do the best work, what we have to do. All we can do is just keep producing. But that raises a puzzle to me, because to think about what happens if I produce a great hit? Because if I produce a hit, I would want to think, I learned the secret, has some recipe, and put me on the map, allow me to attract funding and students. All of them should help me to do another work, a great hit, right? But the random impact rule paints a different picture, is to say, well, after your greatest hit, your next paper actually is more likely to be mediocre than spectacular, because regression toward the mean. So the puzzle cracked open when we look at not just your best work, but your second best work. So what we see here is to think about, if I know where your best work is, where will your second best work be? And what we're seeing here is a clear diagonal pattern. So this means if I know where your best work is, I know very well where your second best work is. It's just around the corner of your best work. And so similarly, you can do this for the second best work, third best work. What you see is that while the timing of each scientific hit appears random, the relative timing follows rather predictable patterns. We also want to see whether these great hits all come together back to back in close succession in sequence. So we also measure the winning streaks. And what we see is that real careers are characterized by high impact works occurs in sequence, much more likely than we would expect randomly. So this raises a question that, what mechanisms are responsible for the observed cluster of hits in real careers? What we find is that the most likely explanation is this ubiquitous yet unique hot streak period that emerges randomly in the career. So the way to think about this is to say, well, if I have, if you start your career at a certain level, and then every time you produce a work, you're drawing from a certain distribution, that's a gamma 0 here. And then you progress along, and at a random point, a certain point in your career, you all of a sudden elevated to another level. It's like you're not yourself anymore. You're all of a sudden producing at a much higher level than typical. And you stay at that level for about 4 to 5 years, and then you fall back to where you were before. Okay. Once we assume this very simple variation in the career, what we find is that it actually can explain all the patterns I've shown you earlier in terms of real career histories. But what's really interesting about this model is then we can fit this 2 real careers, and then learn a little bit about the properties of hot streaks in these careers. And there are several take-home messages that are useful for all of you. First, we find is that hot streaks are actually rather ubiquitous. Around 90% of people have a hot streak. But it's also usually unique. Most people have just 1 hot streak. Much fewer people have 2, and people who have 3 are extremely rare. Second, hot streaks don't last forever. It lasts about 4 to 5 years across these careers. And third, it appears unassociated with any productivity change. In other words, you don't really produce more during hot streak. It's just what you produce seems substantially better than we would expect otherwise. So hot streaks are highly relevant in science because future impact is critical for hiring, career advancement, research support, or other decisions. For example, we find that the timing and magnitude of hot streaks dominate a researcher's career impact. So this means that if we ignore the existence of hot streaks and their singular nature, this may lead us to systematically over or underestimate the future impact of a career. But a central question remains, that is, what is the mechanism? And this is a question I raised shortly after publication of the Nature paper in LPAD to Wall Street Journal, because to me, this is a central question. If we can answer this question, it could potentially allow us to answer a range of new questions. For example, can we anticipate the start or the end of a hot streak? Can we create an environment to facilitate and promote the onset of hot streak and to extend it when it emerges? For someone who has had a hot streak, can we treat it as an indication of their true potential and think of ways for them to realize that potential again? So, we have been hammering around this question for a couple of years. I'm more excited to share some new progress that was just published 2 weeks ago. So I'm very excited. And this insights really came from before the COVID time, when I was visiting Amsterdam and I was walking around the Van Gogh Museum, and I know Van Gogh was a data point in my data where his hot streak happens around 1888 when he moved from Paris to South France. And so while walking through the museum, I feel like as an amateur, I can even see there's some differences in terms of the work he produced before and the work he produces afterwards. So that made me thinking, if we really want to understand what happens around the onset of hot streak, we ought to look at what was produced before and what was produced afterwards. So this made us collect a range of new data sets, including what the artworks are for these artists. And so in this case, we collected about 800,000 images of artworks from all the online sources we can find, as well as about 80,000 plots and casts information for movies. And then for the 20,000 scientists, we collected about 1 million publication records associated with each paper. So in this case, but quickly you realize, this is impossible to do for any human being to think about 800,000 images. And this is where, sort of this the new advances in deep learning become very useful. So in this case, we want to think about to examine the art styles of each artist. We use a transfer learning approach and connect an embedding to construct the embedding for artworks using deep neural network. Specifically, in this case, we applied a pre-trained VGGNet algorithm, which is one of the best known algorithms for image recognition. And then we apply it to the images of artworks. And then we connect it with an additional neural network with fully connected layers to classify art style labels in our database. So once we do this and sort of the model predicts, well, what is the art style? Then we can actually start to dissect the neural network under the hood to say what exactly this neural network is seeing out of this painting. Here we can actually analyze the lower layers of neural network, which captures low-level features such as brush strokes and line orientations, as well as higher level features, layers that captures objects and themes and shapes of the artwork. So if we combine the lower level features and high level features, this will give us about a 200 dimensional representation, high dimensional embedding of each artwork. Similarly, for movies, we can train a word embedding on the plots of the movies, as well as a deep neural network on random walker on the networks of casts to understand a node embedding of casts. In this case, then we combine them all, again, having a high dimensional embedding of each movie. For scientists, we build on a recent paper to analyze their references cited by each paper, and then to figure out what the topic of each paper is. Okay, once we have this machinery, then allow us to test the one central hypothesis is to think about this strategy of exploration and exploitation. So of the myriad of forces that may affect career progression and success, the strategies of exploration and exploitation have attracted enduring interest from a broad set of disciplines. So this made us wonder, is there any relationship with health streaks? So in this case, then we can take all the careers, align them based on when the health streak occurs, and look at what was produced before and what was produced after. We apply clustering algorithm to understand what are different styles and topics, and then we measure the entropy of those works, styles, and topics. And what we're finding is three simple primary findings. So first, we find that before a health streak, entropy is systematically larger than expected, indicating that individuals tend to diversify the topic they work on before a health streak begins. And this is consistent with an exploration strategy in the period leading up to a health streak. Second, following the onset of the health streak, entropy measured in real careers becomes significantly smaller than expected, suggesting that individuals become substantially more focused on what they work on. And this is better captured by exploitation strategy. Third, despite the differences in the three types of careers we studied and the methodologies to examine their outputs, the observed association between exploration, exploitation, and health streak appears remarkably consistent across all these domains we studied. So what's interesting is that we find neither exploration nor exploitation alone is associated with health streak dynamics. Rather, it is the shift from exploration to exploitation that closely traces the onset of health streaks. So one plausible explanation is that exploration as a risky strategy increases the chance that individuals stumble upon groundbreaking idea. And the subsequent exploitation then allows the individual to focus, develop knowledge and capabilities in that area, and build out the discovery further. Importantly, these findings suggest that both the ingredients of exploration and exploitation seem necessary. So this supports this notion that not all explorations are fruitful, and exploitations in the absence of new ideas may not be as productive. So on the other hand, the sequence of exploration followed by exploitation may facilitate the emergence of new insights by incorporating new insights into a focused agenda. And this exploration positioned before exploitation may therefore serve to expand the individual's creative possibilities. So the paper was published 2 weeks ago. Feel free to check it out. And I guess the first lesson I offer here is there is hope. And this is especially evidence in John Fan's career, who was forced retired from Yale at age 70 and then set up a new lab in Virginia Commonwealth University, embraced the beginning of his health streak that had recorded the discovery of electron spray ionization, which won him the chemistry Nobel in 2002. So in his career, we see the most important and uplifting implication of this phenomena, health streak phenomena, is that, to think about the conventional view is to say our best work occurs in mid-careers. And once we pass the mid-career, our hope for a breakthrough start to dim. But health streak phenomena contradicts this, indicating that instead, a health streak can emerge at any stage of your career, resulting in a cluster of high impact work. So this means, every gray hair we may have, it does not by itself make us obsolete. As long as we keep putting work out there, our health streak could be just around the corner, just out of sight. So this means we may not all have Einstein or Feyn's impact, if we keep trying, our own version of a miracle year may still yet to come. And then to think about a strategy that's associated with how the health streak starts is to think about exploration followed by exploitation in terms of how it may facilitate the emergence of your health streak. Okay, so now I'm going to shift gear a little bit and think about the problem with this. What I just described to you to think about individual success is that, you know, science is no longer about the lone geniuses working alone making these discoveries. Rather, the high impact work is disproportionately emerges from complex network of innovators working together in larger teams. So this is, I want to quote one of the most canonical studies in the field. It's a research done by my colleague, Brian Woodsey, Ben Jones, as well as Stephen Woosty back to 2007, where they documented a remarkable fact. That is one of the most universal shifts in science and technology today is the growth of large teams in all areas of research as solitary researchers and small teams diminishes. So one example, poster child example of this is to think about LIGO experiment, the detection of gravitational waves. And this is a remarkable achievement by large teams, and it's a feat that no small teams or individuals can ever hope to pull off. You know, indeed, the discovery was coined the discovery of the 21st century. It won a Nobel Prize 2 years after the discovery. When the paper was published in PRL, it had over 1,000 authors on this paper. So partly for this reason, this movement toward larger and larger teams has now become a self-fulfilling trend. The research shows that at NSF, when two projects are equally promising, program directors more likely to fund the larger team one on the promise that larger teams will offer more innovation. But at the same time, there are reasons to believe large teams may not be optimized for innovation. Large teams, just like large business organizations, may focus on sure bets with large potential markets, whereas small teams that have more to gain and less to lose may undertake new untested opportunities. So this makes me and my collaborators wonder, you know, is bigger always better? So here we look at about 43 million papers, science teams, 5 million patents, teams of inventors, as well as 16 million code bases, so teams for software development projects. Across all this, we measure a well-established measure in the field called disruption index. So disruption index basically measures of all the works that cite you, how much of them also cite the work that you cited, okay? And in other words, how much do you eclipse the literature that you build upon or amplify and develop that existing literature? Let me give you an example. This is a paper, BTW model paper, it's self-organized criticality, highly disruptive. What you see is that in the future paper that cite this paper, they all just cite the BTW model paper alone, ignoring all the other papers that were cited by the BTW model. In this case, it's a Davis et al. Paper that won Wolfgang Nobel Prize in physics. It has a similar number of citations, 3,000, and this is an empirical demonstration of Bose-Einstein condensation. So although the paper has the same number of citations, what you see is that all these future citations also cite the paper that came before the Bose-Einstein condensation paper. So sort of this means it's amplifying existing thought process. Okay, so so the question then, once we don't want to just apply this measure to all the teamwork products and see how that correlates with team size. Across all the three kinds of settings, we find a nearly universal pattern, namely all the red lines are going up, all the green lines are going down. Okay, the red lines going up basically confirms the existing study, which means as team size increases, the impact of the work they produce systematically increases, confirming all the pre-existing studies. But when we look at the disruption index, what we see is that as team gets larger and larger, the disruptiveness of the work they produce becomes systematically smaller. So what this means is that while large teams tend to develop and further existing ideas, smaller teams tend to disrupt current ways of thinking with new ideas, inventions, and opportunities. In other words, large teams excel at solving problems, but it is small teams that are more likely to come up with new problems for them to solve. So one way to think about this is to go back to a gravitational wave example, is to think about, well, LIGO was the discovery of the 21st century. It was a careful demonstration of prior hypotheses. It was built to validate the discovery of the 20th century, proposed exactly 100 years before. In November 1915, when Prussia Academy of Science first heard the highly disruptive theory of general relativity, it was presented by a single author, which is the ultimate small team. The idea of a gravitational waves and their measurements both move science forward, but they do so in very different ways, right? So this is where the main conclusion is to think about both small and large teams are essential to a flourishing ecology of science and technology. While small teams can drive disruption, larger teams can pick up the ball and engage in greater development of a given area of research. And this is where sort of, Nature put us on the cover and sort of arguing for ecology of research, or ecology of small and large teams work together, right? And so one message then for everyday scientists is I feel like I myself benefited from this finding because I manage teams on a daily basis. And I guess the main lesson here is the bigger is not always better. Because usually when I used to think about this is that as a collaborative person, I used to think, why not add another member to the team? That person may not help, but it shouldn't hurt, right? But our research shows that this is not true. Creating larger teams are likely to shift your focus and outcome from disruptive to developmental. So it really depends on what kind of project you're trying to do. For the most disruptive, innovative works that try to disrupt the new way of thinking, maybe you want to shrink the size of team before you start. All right, so now I'm gonna shift gear again and actually sort of challenge everything I've discussed so far, is to think about, as I sort of study more on the successes of individuals, teams, organizations, and the products they produce, I realized there's a big elephant in the room, which is failure. And to me, this is a very crucial issue, because I all of a sudden realized all these insights about success are mostly based on people, organizations that have succeeded at the first place. And that to me, it was worrisome. So that's why I told my group about 3 years ago that, I'm gonna start looking at failure instead of success. For a long time, nobody believed me until they knew I was serious. And then let me give you one reason why this is, to me, is an important issue. And this, the story is familiar to many people. And this is a story that goes back to World War II, where British Navy invented a new armor. The good thing about this armor is that you can put it on a plane and make the plane bulletproof. The problem with the armor is it's quite heavy, so you can't coat the whole plane with the armor. Then the plane won't take off, right? So where do you put it? That will give you the biggest bang for your buck. British Navy was no dummy. They were like, let's big data to the rescue, right? Let's go to the airports and count the bullet holes. Once you count the bullet holes, you sort of know where you put it. They almost went ahead with the plan until Abraham Wald, the statistician in the department, stopped them and said, guys, what we should do is the opposite, because this data was collected based on planes that were successful enough to come back to the base. So this places you see like Swiss cheese is no problem, let them shoot it. It's the place where don't see any bullet holes is where it's most lethal. So, this is obviously an extreme case where the conclusion got turned 180 when you have the data that only captures success. But on the other hand, I look at the world around us and I examine my own scholarship. I realize, we're studying geniuses of the genius, looking at nature sciences of the papers. I listen to entrepreneurs who have succeeded at the first place and come back, give commencement speech, tell us, you are already naked. What do you have to lose? So, so the effect in this case is probably not as dramatic as the British airplanes, but are we so convinced that conclusions we have about success and failure by only observing the successful cases would not need any correction? So that's more broadly, I want to think about, this question of, have we paid enough attention to failures? So today I want to sort of cover some initial understandings in this domain that has broadly helped us improve the understanding along 2 dimensions. One is to think about are there impending signals in failures that eventually lead to success? Are there things we can learn from failures that can help us succeed sooner? What are they and how? Second is to think about, do failures matter? What's the consequence of an early failure on long-term career outcome? So I want to focus on the second question first. I want to sort of talk about what type of failure that has fascinated me for a long time, which is near miss. Near miss is kind of failure that you almost didn't quite make it, right? So my question is, when the near miss happens, how much difference does it make for your career? And the opportunity came when NIH came to me and gave me all their data, which is just 12 failures. In this case, we have about 700,000 competing applications ever submitted to the NIH. So that includes both funded and unfunded grant proposals. Data span over 35 years, so we can trace some long-term career outcomes. In this case, we're focusing on just junior PIs only. And the nice thing about NIH is that the design of how NIH fund proposal is that when every proposal goes through a peer review panel, and then they come back with a score. And program director basically just line up the proposal based on their score and starting funding the proposals one after another based on the best scores to the worst scores, one after another. At a certain point, they run out of money. That's an arbitrary cutoff. That's called pay line. When this happens, it creates a very interesting 2 populations of junior PIs. That's called narrow winners and near misses. These people a priori thinking about all starting out like an assistant professor 3 years into their lab. These are people like what economists call identical twins, right? They're similar in every way that you see, but after that day, there's a big difference between the 2. Narrow winners now have $1 million for 5 years to study whatever they proposed. Near misses at that point had nothing, right? So the question then is, if we look at many years later, when these people come back for a job interview, who do you hire, right? So, this is the question that used to have a trivial answer is, so hire the one who succeeded. The logic is, even though these people are the same people, rich get richer, success breeds success. Now, we just wanted to measure, their CVs, imagine their CVs in the next 10 years. Look at all the papers they publish and see how important these papers are. So I'm going to first measurement is to think about this ISO standard measure in my field called a hit paper probability. So the idea here is to say, out of all the papers you publish in the next 5 years, how many of them ended up being a hit paper, defined as in your top 5% citations in the same field and year. What do we see is that narrow winners publish hit papers around 13%, much, much higher than typical scientists in their field. And this is the idea that, being a narrow winner at NIH, this is not a walk in the park, right? This is actually a very big achievement. Near misses, on the other hand, in the next five years, publish hit papers at 16%. If you look at the papers from year 6 to year 10, you see a similar gap persists, right? But so what this means then is interesting is that, paradoxically, near misses, the one who failed, actually systematically outperform narrow winners in the future. So when I saw this, I was like, this can't be right. Maybe something is wrong. So I basically work with my postdoc that varies all kinds of measurements we can find. Every time we vary our measurements, we find the same conclusion, right? So if you look at the number of papers they publish, you see that both groups have a similar number of papers. So the picture here is to think about near misses had fewer initial grants, but they ultimately published as many papers. And most surprisingly, they produced work that garnered substantially higher impact. So this obviously begs the question of what is going on here. So one idea here is to think about the screening mechanism, which is, it goes somewhere like this. Early career setback is actually quite devastating. So when that happens, it sort of differentially knock out 2 groups of people across the 2 groups. So there are more people left in the failure group. And this actually can be validated from data. What we see is that it is associated with about 10% attrition rate difference between the two groups. So this raises the question of, is this a quit versus grit? Is this about your just better half of the population that are still here, or do they actually become a better version of themselves because of the failure? So, how do we test this? It's too late to call these people and say, hey, come back for some, publish some papers, so let's see how you do. But one thing we can do is to sort of what the economists call a conservative estimate, is to think about, okay, let's artificially remove people from the narrow winner group so that whoever that are still here are at the best position to compete with the near miss group. So if we do that adjustment, what we see is that the narrow winners performance improved by construction, but that improvement was not sufficient to cover the gap that we observed. So this sort of offers among initial empirical evidence that sort of shows the Nietzsche's classical phrase of what doesn't kill you makes you stronger. So the lesson here is to think about this idea of failure as a counterintuitive predictor for future success. And just to quote Shinyang Yamanaka, the father of iPS cells, regenerative medicine, when he won Nobel Prize in 2012, he says, I can see any failure as a chance. Okay, so last 5 minutes, let me show you just one last study very, very quickly. And this was sort of motivated by this commercial. Let me just play this quickly.
I've missed more than 9,000 shots in my career. I've lost almost 300 games. 26 times I've been trusted to take the game-winning shot and missed. I've failed over and over and over again in my life. And that is why I succeed.
So we know that success is often preceded by repeated attempts that fail initially. But how exactly do we fail over and over to eventually succeed or not? Because the reality is that only some histories of failure lead to success. So which failure patterns ultimately yield results? Conventional explanation on this issue centers on luck or differences between winners and losers based on their learning strategies or individual characteristics. But our new research shows that the answer is not that simple. In this case, we analyzed 3 kinds of data sets, including NIH grant applicants trying to get a grant, didn't work, try another time, didn't work until they got the grant. Or serial entrepreneurs found a company, didn't quite exit, found another company until they have a successful exit. Or terrorist organizations thinking about launching an attack, but didn't make a dent, didn't claim any causality, launch another attack until they eventually succeed or not. Across all these cases, obviously very diverse settings. So we want to think about building a common mathematical framework to analyze, to understand failure dynamics. In this case, we developed this model, which we call the K model, that basically try to see a failure as this wonderful thing that gives you 2 crucial assets. First of all, you failed, that means you have tried, right? So that means you've got something to reuse and learn from if you try again. Second is that if you failed, that means you have some feedback, tells you some part that you did well, some part you didn't do well. So when we think about this past experience and feedback, so what we can think about is, as we're thinking about try again, we can compartmentalize this attempt into different components. And then basically think about in the past components, how good they are, and should we update it? Should we create a new one or just keep using the old one? Okay, so if we just assume this, then we can actually sort of solve, how would your performance and efficiency look like as you try again and again after each failure? And what we find is that, we realize how much we benefit from failure actually does not follow a smooth pattern, smooth path as a function of how much we learn from the past, but characterized by a first order phase transition that separates stagnation and success region. So in the stagnation region, people learn a little bit about fast failure, but this learning is not sufficient. So on net is almost like you're not learning at all. So in this case, people hit a very early terminal saturation point and not engaged in any intelligent patterns of improvements as you fail over and over. So in many cases, they actually throw out all the prior attempts altogether, although some of them might have been actually on target. So when you learn just a little bit more failure, at least want to pass this tipping point. So all of a sudden you enter the region of progression. So in this case, these individuals can engage in the intelligent improvement by through incrementally better attempts and ultimately marching towards victory. And so those who eventually succeed in this case, they fail much faster, are increasingly fast with each attempt. And they reuse previous component efficiently rather than discarding the baby with the bathwater as the other side of the tipping point people do. So in this case, the important part is that the idea of phase transition means that small changes around this parameter can make a very big difference. So in this case, what we see is that, two individuals just along these tipping points, they may have the same individual characteristics and learning strategies, but they may be faced in terms of very different realities between them. So what we see is that, despite the simplicity of the model and the diversity of the domains we study, we find that people across fields, terrorists, entrepreneurs, scientists, they predictably diverge into the success and stagnation groups. Although, despite the fact that these groups are of actually rather similar size and initial characteristics, okay? So what this also means that these groups also follow fundamentally different temporal patterns that are distinguishable at an early stage. So in this case, sort of the main lesson here is to think about don't just fail fast, but fail faster. So this is the case that think about both as a strategy and a diagnosis. In terms of strategy, this sort of it reinforces the importance of rapid prototyping. Think about, see what works, adapt, and then stay focused on what needs to be improved. It's also diagnosis. So think about if you're not failing faster over time, it may mean that you are stuck in the stagnation region, making the wrong improvements while appearing busy and productive. So in this case, you want to re-examine if these efforts are targeted at wrong areas and not missing the critical transition to success. So let me stop there, and grateful for a wide range of funders that support our research made it possible. Feel free to visit my website and also the center website for more information. And today, the main research is mainly sampled based on the audience as an individual scientist, but there are a range of other findings in this field that sort of speak to a range of audiences. So feel free to check it out. So let me stop there in case there's any questions.
Sure, thank you very much, Dashun. There are already a couple of questions in the YouTube chat. If you have, if you would like to ask, please type your questions and I'll read them. I have one question. So, for example, in many countries, in many disciplines, there are finite resources. So you want to, let's say, optimize how you spend money, and some people might think, oh well, since we have only few very good scientists or sports people or artists, let's just fund the good ones and let's save the money from those that are not so good. But that assumes first that you can detect somehow which ones will be the good ones. From what you've shown, it seems it's not so clear that such a method exists. So the question is whether is it feasible to kind of, let's say, if we want to improve science in general or art in general or sports in general at a country level. So let's say a country says, okay, we want to get more gold medals in the next Olympic Games. Is there a shortcut to say, okay, we'll select this type of people, or simply the solution is we just need more sports people, even if we get a lot of not so good sportsmen, so that from those we will get a few which are very good?
This is a great question. I don't want to confuse sports with innovation or science. I actually believe they're quite different. So let me sort of center the discussion around science and innovation. I think the question are twofold. One is, if we think there is no way to increase any budget or investment, if you think about fundamentally it's a finite resource and it's fixed, then we want to think about how to optimize this portfolio, optimizing both productivity as well as surprises. And I think that in that case, what the field is offering is something I think is urgently needed, because it has been allocated ever since there's a science funding. And how are we relocating it so far is mostly from different countries. It's a gut feeling from some experts without looking at any data. Right. So in this case, I think what we're offering is to say, well, we should look at data and actually analyze it a little bit more. And in this case, hopefully, as we analyze data, it will also help us counter some biases, including diversity issues, gender biases, underrepresented minorities, and thinking about how do we have a balanced portfolio that balance both productivity and the disruption, right? So that's one thought, but that's actually not my position. Here is my position, and that's consistent with a recent paper written by Ben Jones as well as Larry Summers. So the idea is to say, so how much science should we fund? So this is where I believe science and sports differs fundamentally. Because what science creates is a public good that in the end will improve human conditions. So what this means is that any discoveries in science would eventually may have some social returns to society. So recently economists calculated exactly that, is to say how much of a social returns are there for scientific investment. And the answer, it depends on who was doing the calculation, but the conclusion is quite consistent. The answer is every dollar we put in, it generates about $5 return to society, okay? Now the argument is to think about, if you have a secret machine that every dollar you put in, you have a $5 spill out of the other side. If that's the case, I just can't imagine why don't we put all the money in there? Let alone it's just 2.something% of GDP. So I think that's kind of the broader discussion we need to have, is to think about, if we really have this kind of powerful machine that you put $1 and you have $5 to benefit the society, then I think we're not putting enough to this. But this is again sort of illustrates why the field is important, to help us understand, sort of what is the spillover, what is the social return to human society as we invest in science.
Yes. Well, Ricardo Arencibia asks, what he says, excellent conference. Have you tried in your research to characterize interdisciplinary or transdisciplinary research? What are the challenges of this kind of studies for the data scientists?
So what's the first part of the question about conference?
No, have you tried to characterize interdisciplinary or transdisciplinary research?
Yes, I have. I was just working on a paper this morning about this, but a lot of other people have also looked at this, and this is a question that's been very sort of on top of our mind. I think the general conclusion is we do have evidence that interdisciplinary research tend to garner high impact. We also have the evidence, very clear evidence on interdisciplinary research face growing penalties in terms of they systematically are characterized by lower funding rates. So it's very difficult to get started. And I think sort of these are the sort of speaks to the pros and cons of interdisciplinary research.
Yes, Humberto Carrillo asks, a very interesting talk, which do you consider the greatest achievements in the field of science?
Oh, well, what's the greatest achievements?
Yes.
Can you repeat the question?
Yes, which do you consider the greatest achievements in the field of science?
Oh, that's a great question. the greatest achievement is what we're going to achieve next year. I think that's the greatest achievement. It's very hard to say right now. We're seeing a lot of very promising initial achievements. So it's very rapidly evolving as well. So and this was sort of supercharged by also the development of artificial intelligence and all the other domains. So I think what hopefully is we're going to see more and more exciting achievements as we go on. Yeah.
Yep. I have another question. If you're in a hot streak, like scientists or directors or artists, is there a way to extend it, or the best strategy would be to kind of start exploring again so that hopefully you will exploit later? I mean, because I can imagine that you can exploit only for so long some innovation.
Right. Yeah. So what we're finding is for people who have 2 house streaks, we look at, okay, what happens in the second one? And what you're seeing is that in the first house streak, you have exploration and then exploitation, and then you go back to normal in the end. And then before the second house streak, you again have this exploration followed by exploitation. Sort of this A/B punch seems to show up again, more likely than chance, but statistically significant. So that's something to consider. We actually don't know. We don't have the answer for how to extend it. I think the main reason is also this kind of research is necessarily observational. So we actually don't have the causal evidence for how it begins or the ends. What we really have is a regularity that we observe from data that seems to predict when it happens.
Yes. Juan asks, according to this new vision, what would be the current definition of science?
According to what? Can you say it again?
Or better said, how would you define science?
How would I define science? That's
that's a tough one.
That is a tough question.
Like asking a biologist, how do you define life?
I think I have to get back to you on that one because I want to think more carefully about that. I should have an answer, but it's a deep, very deep question. So I let me think more and get back to you.
Yes. Another question. There are already methods for increasing impact in science arts. Sorry, let me rephrase. Are there already methods for increasing the impact in science or art of our work? And if so, how can we measure that impact?
The measurement of impact is a heavily discussed issue. Basically, if you think about the field of scientometrics, it's a field that basically dedicated to understanding measurements and its perils. So it's been sort of discussed very extensively on different measures and then the unintended consequences of different measures. So almost all measures have its own limitations, and every measure is necessarily imperfect. But what we're finding also is, if you think about the impact measure for science, these measures all correlates quite well to a certain degree, and they each capture certain dimensions while ignoring other dimensions. And I think what the field is contributing is to the debate that, how to think about this measure, use this measure in a more responsible way. And I think that's kind of what's important contribution of the field, especially for science decision makers. So if you think about, institutional leaders like your deans, department chairs, or VPs of research, these people are often familiar with the deluge of metrics right now going on, yes, but they sort of don't have a cohesive framework to think about which one to use, which one to avoid. And in some ways, the hope is the book will also offer them a sort of a quick guide on how we think about these metrics by offering data behind these metrics.
Great. Ricardo Nenciba, he's a colleague from the Centro de Ciencias de la Complejidad, and he asks, well, there is a project at the C3, Complexity and Science of Science, and one of the goals is to design indicators to determine the social impact of science. Has your group had any progress in this issue?
So I mean, one project we have been working on, and as a direction in the lab, is to think about what are the impacts of science outside of science. And that's something we have been thinking a lot. And I think there are more and more data available now that capture different aspects of human society and how science is being cited and used in this context. And this includes earlier work we published about how science is being cited in policy documents, in the houseways of governments across the world. It also includes sort of how science is cited in marketplace applications, such as patents. It also includes how science is being consumed in media reports, thinking about the public perception of science. So I think all these dimensions are now becoming available, and we've been sort of looking into them, but I think this is sort of the ongoing area of research.
Yes. Jose Luis Jimenez asks, last century, researchers did not have the pressure of journal impact factor. Have the current time of hot streaks between, have the current time of hot streaks been affected by the impact factor in this new century? Or I think you can rephrase this as, is there any difference between hot streaks this century and previous century, or a century ago?
So our data is mostly like 1950 to 2009, I think, sort of in terms of careers. We did do sort of separate people by cohorts, and we don't see much of a difference. So that's kind of the temporal stability of these results.
Yeah. Well, thank you very much again, Dashun. It has been a very interesting talk. And well, again, everyone, buy Dashun's book. It's great. Well, there's one last question by Ibis Lozano. What is the impact that the citations jump decay pattern has on the relevance of research over time?
Is that about a citation, jump and decay pattern?
I understand that usually most of citations people receive are within 2 years. So you get like lots of citations, and then does that pattern has any relevance of research over time?
Yeah, so this is something that we published very early on, starting from a 2013 science paper to sort of thinking about complex network approach to model how citation dynamics evolves. And what we see is actually, if you look at the individual's paper citation dynamics, is characterized by a remarkable diversity. But what we actually realize is that despite that diversity, there is a remarkable amount of regularity behind it. And sort of then we have actually a closed form model to capture the dynamics. So it seems to us then there's a lot of regular patterns beneath this apparently noisy patterns that we observe. Recent work by Carlos also extended this idea to think about universality and rank dynamics, which is something that I greatly enjoyed in the paper. I think right now it's still on archive, and I think everybody should check it out.
Yes, we're in the
published.
We're in the third round of reviews.
What's that?
We are in the third round of reviews. It's always the third referee.
Okay, well, best of luck. Best of luck.
Yeah. Okay, so thank you very much again, Dashun. It's been a great pleasure, and hope to meet you soon in person.